honored to be invited to this workshop. And so I boldly announced this title, this talk on random quantum marginals. In fact, what I'm probably going to do is I want to start out just defining what is known as the quantum marginal problem, and I want to present like some general theory, some general ideas that people have used to tackle this problem, and then in the end I want to maybe briefly comment on some say preliminary works that we've done on a kind of a randomized version of a quantitative version of this problem. So so maybe let me just jump right into it and define what is the one-body quantum marginal problem. And well, maybe before I do this, actually, let me just briefly recall of that. Of course, a couple of terms that I will use all the time. Of course, a density matrix you all know is a semi-different operator on some Hilbert space of trace with trace 1. And I call this thing a pure state if it's rank 1, so if it's just a projector onto a vector on the one-dimensional subspace in Hilbert space. So it's called a pure state. Well, if rank 1, if you like. So then I will happily use a Dirac's notation to denote this projector as follows, where psi is a vector in Hilbert space. Okay. Now, what is a reduced density matrix? So if I have a if I have a quantum mechanical system that's composed, say, of two subsystems, then it would be described by the tensor product Hilbert space. And now suppose that I have a quantum state on the full system, so on this tensor product Hilbert space. Then I could ask, what is the effective state? What is the density matrix describing the subspace, the state of the subsystem? And this is given by the so-called reduced density matrix. So if I suppose I have a state rho AB on some tensor product of two Hilbert spaces, HA tensor HB. Is this readable for the size?
A little bigger for me.
Okay. All right. So if I have this joint state of the quantum system, then I can define the reduced density matrix, say of the first factor of the first system, rho A. For instance, by the following relation, I can say, well, it should be the quantum state such that for all observables OA, this is precisely the same as computing the expectation value of OA tensor the identity on the V system. So say Hermitian, if you like. So this defines this object called the reduced density matrix. Now you could ask, well, what are the possible reduced density matrices of quantum states? Now, of course, you can always find a quantum state that gives you a certain reduced density matrix, but now you can basically ask this question in parallel for all the subsystems. And so this gives you the following question. Check what I call the one-body quantum marginal problem. QMP. So what this asks is, suppose you have a pure state. So you have say, well, for concreteness, let's look at a quantum system composed of 3 parts, and I will comment on why I look at 3 parts and not just 2. And so suppose I have this. So this is my big quantum system. I have like 3 particles A, B, and C in there. So 3 subsystems. And suppose that the overall state is a pure state. So it's a projector onto some vector in Hilbert state that I denote by psi ABC. Now, from this pure state, what I can compute are the reduced density matrices, say, of the single particle. So this would be rho A, rho B, and rho C. And now what the problem asks you is, what are the possible combinations or triples, rho A, rho B, rho C, that are compatible with the pure state? Okay, so which rho A, rho B, rho C are compatible with the pure state? And so this I think this term, quantum marginal problem, has been introduced by Alexander Klyatchko, who's also given the first explicit general solution. And I mean, as we go along, I'll maybe try to explain to you a bit more carefully what he did. Sometimes. That's right. I mean, sometimes I would like to impose additional statistics. Say, for n identical particles, then I would ask the state to be in the fermionic subsystem. And of course, some of you will know that actually there's no reason to look only at the one-body instance of this problem. One could ask, for instance, and one could maybe also relax this purity assumption in that case. One could ask, when are 2 reduced density matrices, say rho AB and rho BC, compatible with each other? And so yes. So I was thinking of starting out that way, in essence, and trying to reduce down there. Then I thought, in the interest of time and kind of, since this is a maybe more mathematical workshop, I will not so much motivate this. But maybe let me say that the two-body problem is maybe the one that would be physically most interesting, but it's also one where we can prove that the problem is NP hard. And so, in some sense, it's actually even hard for quantum computers, supposing such a thing will ever be built. So in some sense, we want to study a toy problem and learn about its physical relevance, say, and its mathematical structure. And somehow one crucial aspect of this one-body problem is that in the end, this question only depends on the eigenvalues of rho A, rho B, and rho C, which is not true for the general problem. So why is that? So maybe let me first write this down. So only depends on the spectra, collective eigenvalues lambda A, lambda B, lambda C. And so why is that? Well, if I take, say, if I take unitaries UA, UB, and UC on these three systems, and if I apply their tensor product to this, to say a pure joint of a pure global state, then what this will do to the reduced density matrix is this will just conjugate them by this unitary. And so if I can achieve one triple of reduced density matrix, then I can achieve all triples with the same spectrum. So this is why, in the end, the question only depends on the eigenvalues. And yeah, so in a sense, this is why we can solve the problem. Yeah, maybe I kind of said this at the beginning. Most of the things that we'll talk about are not, of course, what I've been working on, like my contributions. So this is going to be more of a general talk, and maybe I will sometimes tell you about the kind of directions that we have pursued. Very well. So let me maybe give you one example of what I mean. Well, saying that this problem is not completely trivial, and well, maybe note that it would be trivial if I wouldn't require this purity over here, because then I could, of course, just take the tensor product of these reduced density matrices. So it's really the purity of the global state. Did you raise? No? Okay. Very good. So here's an example. So I'm again the three-partite situation. What I claim is that if you take the maximal eigenvalue of the first system, yes, like that, plus the maximal eigenvalue of the second system, then this will be at most 1 plus the maximal eigenvalue of the third system. So this is one maybe non-trivial constraint. And here's a hands-on proof of how one can see this. And the proof basically proceeds by variation argument. So take this maximal eigenvalue, the sum of maximal eigenvalues, and just write it as now we'll probably get into trouble with space. Okay. That was not so clever. So just write this as, the maximal eigenvalue is the maximal expectation value of a projector. So this is max, trace rho A, project onto A, and I will now become sloppy and use this notation. All right. So now let me rewrite this in terms of the global state. So what I'm saying is take two unit vectors and maximize over all these choice of unit vectors. Okay. So I still have two of these unit vectors. And I'll write this as rho AB times projector on A, times for the identity on the B system, plus the identity on the A system, times the projector on this unit vector B. Okay. Now I can fight with the blackboard for a second. Right. Now what I can do is I can do kind of an inclusion-exclusion principle. So I can expand this identity as the projector onto phi A plus the projector onto orthogonal complement and so on. And so if you kind of collect the terms together, you will see that, well, there's one term missing, namely the projector onto the tensor product on the projector onto the complements. And there's one term too much, namely the projector on phi A tensor the projector onto phi B. And if I just, if I only want to get an upper bound, I can just add in this missing one. So I guess is less or equal to max phi A phi B. Trace rho AB tends to be identity plus. And now that's this guy that I had twice, but I already have it once in the identity in AB. Phi B. All right. So now I'm almost done. Now I relax once more. Oh. Yeah, I'm physically struggling. I'll try. So what I want to do now, you know, this is just one. It's the trace of the density operator. So this is good. On the right-hand side, what I have is the maximum over projectors onto product states. I'm sorry, but there's plenty of space in so let me just rewrite this again. So this is the projector onto phi A tensor the projector onto phi B. And now I can, of course, upper bound this by looking at projectors onto tensors that are not tensor products. So this is a projector onto phi A tensor phi B. Now I can relax this, and I again get an inequality by looking at projectors and arbitrary vectors in this tensor product Hilbert space. So on the following object, phi AB, phi AB. But this is the maximum eigenvalue of rho AB. And now the maximum eigenvalue of rho AB is equal to the maximum eigenvalue of rho C, because rho ABC is a pure state. So this is kind of an it's kind of saying like the left and the right eigenvalues. It's kind of something like this. So this is actually the same as 1 plus lambda max C. Okay, so this is very hands-on elementary proof of this inequality, but in many ways the general solution, at least one can write down, one can recover the general solution by a similar variation argument, where one kind of, instead of just optimizing over, pure states, so vectors in projector space and their tensor products over say, Schubert cells and some flag variety. But I think this captures the spirit rather well. All right, so this, So now what I should of course say is that the type of constraint that I did just derive as a linear inequality on these eigenvalues. And we will see that this is not an accident, but rather that the general solution to this problem will always have this form. So it will be given by a finite set of linear inequalities, which is kind of not obvious, I think. It is maybe not even obvious that the solution is, should at all be in some sense convex, because okay, so maybe let me just draw a little picture that visualizes this over here. So let's take C2 tensor C2 tensor C2 as the first non-trivial example, and let me maybe plot this, these inequalities in some coordinate system. So what I plot here are the maximum eigenvalues of A, of B, and of C. So maybe I shouldn't write. So this is probably not large enough. Okay. So this is the maximum eigenvalue of the A system, same of the B and of the C system. If I look at C2, also at qubits, and the maximal and minimal eigenvalue, of course, they sum to 1, so I just need to plot one of them in this graph. And the maximum eigenvalue is at least 0.5, it's at most 1. So I get this little diagram. And then now it turns out that if one plots these, if one uses this inequality in its permutations, one gets basically the following object. Well, it's like a tetrahedron, like that. On whose base you put another tetrahedron, kind of like this. So it's really, so I hope I drew this in a useful way. So it's like this nice object. Okay. And so in general, the solution will always have this form. And so again, what this says is whenever you pick a triple of maximum eigenvalues, whenever you take a quantum state, it will lie inside there. And actually for qubits, this is the only condition for 3 qubits. Okay. So yes, let me just say this again. So maybe it's not obvious from the statement of the problem that the solution should be convex, because the set of pure states, it's a projective space. It's not typically convex. It could be, say, a sphere, or well, it could only be a sphere in 2 dimensions. But still, like if you mix 2 pure states, you will not get a pure state. So it's not clear that you can mix stuff, and so that something should be convex. Now the second problem that I might or might not talk about is this what I call maybe the random quantum margin problem. Thanks. Yes, this is going to be the random quantum margin problem in a sense. So no, we don't know it. I mean, we can't count them, but what we can ask is basically if we take a random pure state, what is the distribution of these row A, row B, row C? And this is what I fancily call this random quantum margin problem. That's right. So if you take such a psi ABC, so pure state at randoms, and random, what I mean is the Liouville measure on projective space, or the unitarily invariant measure on projective space. Then you get, you get random variables row A, row B, and row C, or equivalently their spectra, and you could ask what is the distribution, or what is their joint distribution, in fact. And so the difficulty is again in the jointness. So the left-hand side problem was trivial if I didn't ask for triples, but if I wouldn't have asked for triples, and similarly here, the problem is well known if I don't ask for the joint distribution. Because in the end, what you will get is that, say, row A is I guess it's called a normalized Wishart matrix. Now, what you will get in that case, if you only looked at row A. Very good. And so basically, so now I want to talk about maybe some unexpected mathematical structure, namely geometric invariant theory, and well, which is kind of a maybe branch in mathematics, if you like, a branch in algebraic geometry, which people have. Which is maybe the only tool that people know for attacking these kind of problems, which is kind of interesting. And I should say that there's a similar problem about spectra, namely Horn's conjecture, or Horn's no longer conjecture, which asked about, if you have two matrices A and B with certain eigenvalues, what are the possible eigenvalues for their sum? And it's the same framework basically that was at the foundations for its eventual resolution. And in fact, yes, this was what Alexander Klatschko worked on first, if you like, and then maybe he used the same methods to look at this quantum margin problem. All right, so let me maybe talk about geometric invariant theory. Okay. So what is the idea? Basically, the idea is that there's going to be kind of an interesting algebraic integrable, if you like, structure behind this problem that gives us some way of attacking it. And the idea is going to be that invariance will play a role, so polynomial invariance. And let me maybe give you again kind of a very elementary, a very basic argument of why that should be so, and then I will maybe without proof sketch the more general situation. And so what I want to look at is, let's look at the following sketch of an argument. So let's. So what I now, sorry again?
Yeah. Well, I didn't understand what you're sketching.
Oh, I want to sketch why there should be any relation between invariance, the existence of invariance, and this quantum margin problem. Although maybe it at least wasn't obvious to me at the time. maybe. Okay, so it's about this problem one, and the second one I will only afterwards talk about. So two, if you like, or maybe actually. Maybe this should rather be 3, and this should be 2. Okay, so let's do 2. And so the idea is kind of, so I was saying that you have this unitary invariance of this problem. Unitary, invariance, if you like, of this problem. So if you can achieve one triple reduced tensor matrices, you can achieve all of them. And somehow what now enters into, into geometric invariance here. What now, the new idea that now enters, let's look at the complexified group. So instead of looking at the unitary group, let's look at GL A times GLB times GLC. I will actually work with SL, but the kind of the same idea. So let's look at this. And so for concreteness, so my Hilbert space is now really CA tensor CB tensor CC. So let's look at this group acting on CA tensor CB tensor CC by tensor products. And let's start with the following assumption. Let's suppose that there exists non-trivial invariant G-invariant polynomial. So P is a non-trivial G-invariant homogeneous polynomial, which, so on some quantum state psi, it is non-zero, unless, just for simplicity, ask that it's 0, I mean 0 on 0. So it's going to be non-constant, so it's going to be non-trivial. It has at least two values. And now,
What is this polynomial on?
on the Hilbert space, I should have said that, yes, on H. So if you like, it's something in the dual of the of a symmetric power of H. So a vector on the, yeah. Right. And so now basically the idea is that an invariant, such an, I mean this is called an invariant, such an invariant gives us a witness of the following statement, namely that if you take the orbit of this state psi in Hilbert space and you close it up, so you take form its closure, then this does not contain the origin of Hilbert space. And so why is that? This is basically because, well, this is a G-invariant polynomial, so it attains the same value on the orbit and then also on its closure by continuity. But, well, so it is non-zero on this object, but 0 here. So it's just separating in algebra. I mean, it's like a separating function in this context. Now, if this is so, then what I can do is I can look at this orbit. So, I mean, on this orbit closure. And I can, so somewhere in this Hilbert space, the origin, these are disjoint closed objects. And so what I can do, I can find a vector of minimal length in this orbit closure. So let's maybe say this is the psi tilde. So we can choose some psi tilde in G psi closure of minimal length. It's important here that I don't take that I don't renormalize these all to norm 1. So I'm really working in Hilbert space, not in projective space. So now what is the point? So now the point is because this object has minimal length, it means that if in any direction that I walk in, its length will not change to first order. Because if it did, then I could walk in the good direction and decrease the length even more. But this object, I mean, the directions that I can walk in, they are given encoded by my Lie algebra because I'm looking at an orbit under this Lie group. Yes. Yes. So it turns out that it is unique up to unitaries. Yes, as you would expect. Yeah. And so kind of so in fact, I think it's going to be contained in the unique closed orbit inside this orbit closure, and in there's a unique unitary group orbit. Yes, I think. Okay, so what this means is now that for all x, and I will actually only look at self-adjoint elements, and I will not make. I think it will be clear what I mean. In the Lie algebra of this group, so the Lie algebra I denote by little g. And the Lie algebra, well, it will be triples of traceless matrices. And I only want to look at self-adjoint ones. So then, well, my norm doesn't change in first order. So e to the t well, maybe I should give a name to the representation. So the representation I denote by pi. So this acts on the Hilbert space. E to the t pi of x. Psi tilde, norm squared equals 0. This is my minimality. But now, of course, I can write this down precisely, and so the derivative is 0. And what this is just psi tilde, pi of x, well, times 2, psi tilde. But now, finally, I mean, observe that the action that I haven't yet written down of the Lie algebra is just in terms of local Hamiltonians, if you like. So what do I mean by this? Pi of x1 to xn is really x1 tends to the identity on all the other systems plus identity on the first. I mean, well, I guess I used A, B, and C, so I should maybe stick with this. xa, xb, xb, xc. xa tends to identity on bc plus identity on A, x of b, so identity on c, plus the last term. And so what this means is, whenever I take a traceless local Hamiltonian and I compute this expectation value, I get 0. And this can, of course, only be if the reduced density matrices are all proportional to the identity. So if their traceless part is 0. Okay, so maybe let me write this down more precisely. This is, of course, the same as trace rho A XA plus trace rho C XC. Okay. And so, so again, so the upshot of this calculation now is that, thus, rho A, rho B, and rho C are all proportional to the identity. So we have now, but what we've now done is established the link between, the existence of invariance and the existence of quantum states with certain reduced density matrices. And now basically the trick is to do this in general. And this is where, I mean, so I'm not going to give the proofs there, but maybe I'll try to sketch a story. So the idea is that, I mean, I present it in such a way as if it was just a chain of implications, but in fact, one can kind of prove the converses as well. So if you have a quantum state, yes, maybe I shouldn't go into this. But I mean, yes. So if you have such a quantum state, then of course it will satisfy these things. So it will be a minimal point. I mean, basically this equation you can read in reverse, no? And then you can find such an invariant polynomial just by separating two closed sets. So basically, you can go in both ways. So converse also holds. And so technically what you use is a theorem due to Kempf and Ness, which basically tells you that if something gets mapped to 0, the G orbit to it is already closed. Hence, you can separate it from 0. This is basically what I just said. And now, moreover, what we also have to do, well, we have to make this work for all the spectra, not only the the identity spectrum or proportion to the identity. So this works for all marginals, so all spectra. And maybe it would be good to write down the general result first, well, specialized to this situation of the quantum margin problem, and then maybe explain to you the one trick that is missing still on the blackboard to actually prove this. And maybe just to formalize things, let me define to what people call the ring of regular functions, which is just a ring of polynomials on some project variety. So maybe let me do this concretely and define, I'll say R of some set X. Maybe I'll just be a bit sketchy. So this is the ring of polynomial functions on. Now I have to make this precise. So before I said I look at polynomials on Hilbert space, that was kind of obvious what I meant. Now in general what I basically look at, what I look at is some subvariety of Hilbert space that is cut out by homogeneous polynomials, what people call an algebraic cone. But maybe it's not so important. Maybe I'll just write down somewhat sloppily on X, and if X is the full Hilbert space, we know what I mean. Now my invariants or my more general objects will live inside inside of this ring. And basically what we said before is if this ring contains an invariant vector, then there exists a quantum state whose reduced density matrices are proportional to the identity. And now basically what we have to do is we have to replace or substitute invariant vector by contains a certain irreducible representation of this group G. And so a non-trivial irreducible representation. This will give us non-trivial spectra for the quantum margin problem. Right. Somehow I always seem to lose space when I do this. Okay, so now the other ingredient is, of course, well, I have to briefly talk. We have to briefly talk about irreducible representation for this group G. And actually, at this point, maybe I want to talk about GL rather than SL. And so let me just introduce some new notation, say V lambda D. By this, I denote the irreducible representations of the group GLD. So irreducible representations of GLA times GLB times GLZ will just be tensor products of VA lambda times, some VA alpha tensor VB beta tensor VC gamma. And so let me tell you what these lambdas are very concretely. So these lambdas are, of course, highest weights. But one concrete way of thinking of them is basically just, in the case of GLD, it's just of integer vectors, or what some people call Young diagrams. So these lambdas are in set D, and so they are, they are little lists of integers, lambda 1 to lambda D, in set D. And some people like to, with weakly decreasing entries, and people like to think of them as little diagrams like this. So Young diagrams. Young diagrams, where this is D, and the first row has lambda 1 boxes, the second lambda 2 boxes, and so on. This is just a concrete way. But it's kind of appealing to think of these highest weights in this way, because this kind of looks like a spectrum. Well, for me nowadays it does. So if you, this is like a weakly decreasing list of numbers. So I can think of it formally as the eigenvalues of something, except that somehow they add up to the number of boxes, so to the sum of lambda 1 plus lambda 2 and so on. So if I divide by the number of boxes of such a Young diagram, I see it's something that looks like a spectrum with rational entries. And so I can compare these two objects, at least formally. Okay, so for instance, to get this Maxwellian mixed spectrum, so proportional to the identity, would just be Young diagrams which have the same number of boxes in each row, and those correspond to the powers of the determinant. And so if I look at SL, I don't see the determinant, hence they're trivial, and hence what I just said, it reduces to the argument I just gave. So okay, I'm still fighting on Blackboard. Okay, so maybe let me now write down the general result, which essentially follows from a general statement of Mumford. So the statement is the following. The set of all compatible spectra, or at least the rational ones, are given by the following set. So you take this coordinate ring, this ring of polynomial functions, say it's in degree k, so the ring of homogeneous polynomials of degree k, on say, I guess, our Hilbert space in this case, and you actually look at the dual. And now in this dual, what you look at are you look for irreducible representations. So say v lambda a tensor v lambda b tensor v lambda c sitting inside there. And now basically you do what I just said pictorially here. So you take lambda a divided by the degree where you currently are, and the degree is going to be the number of boxes in this diagram. So you have lambda a over k, lambda b over k, and lambda c over k. And the upshot is that in this way you get all the compatible spectra. So this is well, not quite a solution of this quantum margin problem, but at least it's an algebraic description. This is the structure behind it. Okay, so does this statement make sense? So this is the dimension of the GL that I look at. Is not a complement or something.
So would you make the statement again? So you're solving this problem 2, I guess, right?
Yes, problem 2. That's right.
Okay.
The first one.
So what's the upshot again?
So the upshot is the set of spectra that I can, for which there exists a global pure state, is and the set of rational spectra for which there exists a global pure state is precisely equal to the following set. Look at the irreducible representations on the degree k polynomials of your Hilbert space. Take the degree polynomials of your Hilbert space, decomposed into irreducible representations. Take the highest weight divided by the degree in which you are. So you get this lambda a over k, lambda b over k, lambda c over k, and these are this is the answer. These are the triples of compatible spectra for which there exists a pure state.
Those are the only ones?
Those are the only ones. That's right. Precisely. And yes, that's right. Yes, and this. Yes, and so basically, I gave you the proof before for this very particular spectrum that was proportional to the which had all entries were the same. And for the general case, one needs kind of one does kind of a shifting trick. So one works in a larger variety or larger representation where what used to be lambda becomes the origin. So one like shifts stuff around. And so maybe let me briefly write this down. So this is what is the crucial ingredient, if you like, to prove this general version, not just the baby case that I said before. Is essentially a variant of the Borel-Weyl theorem, which is kind of the special case of this problem. But let me say what I mean. Let me define things properly. So what part of this theorem tells you is, if you look at the set of all matrices with fixed spectrum lambda, so just like u lambda 1 to lambda d, u dagger. Then turns out that this is if lambda is rational, then this is a nice projective variety. It makes sense to also look at this ring of regular functions as we did before. And the point is that the ring of regular functions of this object in degree k is just the dual of the irreducible representation with highest weight lambda k. So this is basically kind of the pointwise correspondence. So if you take a matrix with spectrum lambda, its ring of functions will be related. Will basically just contain all the irreducible representations given by rescaling this highest weight. And so kind of if you take our trivial argument from before and you kind of shift it by this trick, you get the irreducible representations. Kind of the idea is that an invariant vector and something tensor v lambda k dual will be the same as a copy of v lambda inside the original representation. So you can like shift things around. Okay. Now, sorry?
The random stuff is still missing.
Yeah, the random stuff is still missing, yes. So we'll get there. Of course, since I'm an amateur, and even more an amateur in random things, I don't have maybe so much to say. But kind of the reason I want to write this down is because it has very nice analoga in this quantitative version, this problem 3. Okay. Maybe I should say, so before I do this, maybe I should start with one comment. I should conclude this part with one comment. Namely, so we said before that there's this maybe more interesting problem where one looks at these overlaps. So for instance, at row AB and row BC. And so what we found in some work with my advisor, Matthias Cristando, and a student, Shahinolu. So what we found is basically that one can kind of go a bit further than this one-body problem. One can characterize the eigenvalues of lambda AB, lambda BC that are compatible. Well, actually, we look at A, BC, AB, BC, and the full spectrum. And what this boils down to is, so here we saw what we have to do is we have to take this ring of polynomial functions, decompose it into irreducibles. So now in this more complicated scenario, what we do is we look at 2 decompositions, where we basically, so what we do is we start with this group GLABC, then we can go down to GLAB tensor GLC, and then GLA, GLB, GLC. Or we could go the other way around. So what we saw before is that if we take this ring of regular functions, which is has such a representation, if we restrict to GLA, GLB, GLZ, we solve the one-body quantum margin problem. And now what I claim is that if you actually look more carefully, if you first do this composition into GLAB times GLC, and you compare it with the decomposition in GLA times GLBC, and if you look at the overlap between these two like incompatible decompositions, then you can capture, you can characterize this two-body quantum margin problem. And for some, and quite mysteriously, it gives even an alternative proof of strong subadditivity, kind of basically from these representation theoretic arguments, which is very surprising, I find. But this is maybe just an aside on some work that we did. So now maybe I should talk about the random stuff. Okay. Okay, so again, I mean, so this is going to be a bit, well, yeah, so again, I kind of want to use this invariance. So before we use this invariance to bring it, well, I mean, this invariance and the unitary group, we looked at the complexification. We kind of saw that this gives us some algebraic structure to work with. And I should say that all the known problems to this one-body quantum margin problem, like the one by Kliatschko, they really they start from here, and they analyze this description by one way or another. I mean, Kliatschko looks at kind of the Hilbert-Mumford criterion. I have my own kind of toy approach to the problem, but this is the idea. Okay, so now we want to do something similar in this random problem. So we take, again, what do? We take a project onto pure state, but now a random one with respect to the U, ABC invariant measure, probability measure. So again, my Hilbert space is going to be CA, CB, CC. And I should maybe also say that the finite dimensionality doesn't make the problem any simpler. Maybe it's, yeah. So everything I said is for finite dimensions. So if we do this, we get these rho A, rho B's, and rho C's, which are now random variables. Maybe I call them random marginals or random reduced density matrices. And I want to compute their joint distribution. That's what we said before. So, now, this operation of forming the reduced density matrices is invariant under this local unitary group. So again, this measure will be invariant under the local unitary group. So this will be UA, UB, UC invariant. Okay. And so I can equivalently look at the distribution of the eigenvalues. Yeah, so this is going to be random eigenvalues of the reduced density matrices. And so if you like, these are going to be some probability measure whose support is this polytope from above. Or it's more general versions. And actually, yes, I haven't actually, you didn't catch me, but I haven't actually explained why now from this formula it should be obvious that well, it's not obvious, but why it follows from this description that actually the solution is convex. But maybe you can ask me about this later. So we have this random spectra. So we have like a measure on this funny polytope that we had before. I mean, on its generalizations. And this is what we want to recover. And kind of the idea is, and so I'm not sure. I would be very curious to learn about if this has ever been applied in a different context. I mean, so it's. So basically, the idea is instead of looking at the eigenvalue, so this distribution of eigenvalues, we want to look at the distribution of the diagonal entries of the matrix. And maybe I should also say that these measures, they are called Dustermaat-Heckmann measures in the literature. They have been studied quite a bit, but not for this representation. I mean, but for instance, yes. So this is kind of the general framework that we use. And also the ideas, again, look at the diagonal entries. So study the diagonals of rho A, rho B, rho C. Okay, so each of these guys is a density matrix. And I mean, each of rho A, B are matrices, and we only want to project this measure on the diagonal. And then kind of we want to recover the eigenvalues from this. And somehow the point is that this is possible. And so but it's possible to do precise. I mean, if you have the precise measure, if you have the precise diagonal entry distribution, you can recover the eigenvalue distribution. And I want to maybe talk about that again in a toy model. So kind of so the idea is I have this measure which is invariant under these local unitary groups. So if I can kind of solve the problem for one such orbit, I can solve it generally. So if I know how say a triple of matrices with fixed spectrum, how its projection to the diagonal is related well with the corresponding eigenvalues, then I'm good. And so I again want to look at this object O lambda, so the set of all Hermitian matrices with fixed spectrum lambda. And there's an old result to Harish-Chandra, which is kind of an integral formula for, so what is the object that I want to look at? So I want to look at the probability distribution of the diagonal entries for a random matrix with spectrum lambda. The probability distribution of diagonal entries. And there's a kind of a famous, well, I guess, formula for the Laplace transform, or maybe for the Fourier transform of this measure on the set of diagonal matrices. And if one massages it a little bit, one actually sees that, one actually sees that one merely has to, okay, so they give it in the Laplace transform. So, but if you transform the spec, then what you see is basically if you take this probability distribution of these diagonal entries, and if you take some suitably chosen partial derivatives in certain directions, then you can actually recover the distribution of the eigenvalues, which is of course just the atomic measure at lambda. Okay, because all the matrices have the same spectrum. So the idea is, maybe I should write this down. So if you take sum of all I smaller than j between 1 and d, and you do like delta j minus delta I, you look at the so they're like in the distribution sense, if you like. So this you have this maybe I should of the diagonal entries. I mean, so the diagonals. Yeah. So if I'm okay, so this is like x1 to xd, and I only look at diagonal entries. So these are 0. That's right. So these are the and I have some measure on there. So if I take my test functions, then I take the derivative. So it's like the distribution derivative. These are the coordinates that I look at. And so it turns out that if you do this, then actually what you get is something which is a signed measure, and it is atomic and there's only support at lambda and its permutations. So basically the idea is, so I'm not sure how I should write this. So basically, so I have this funny measure, this funny diagonal entry distribution. Then I take some derivatives over it. And then in the end I get points. One of them is lambda. One of them is lambda with a differently permuted entries and so on. And so if I restrict this to the set of say non-increasingly ordered spectra, what I get is actually something proportional to the Dirac measure at lambda, and that the proportionality constant is a Vandermonde determinant. So maybe let me actually illustrate this in a simple example. So let's look at the set of matrices with spectrum. So let's look at 2 by 2 matrices with fixed spectrum. So topologically, they form a two-sphere, a projective space. So 2 by 2 matrices with fixed spectrum. For instance, you get, let's take the pure states. They have formed this Bloch sphere. And then projecting onto the diagonal corresponds, say the diagonal, say the Z eigenbasis just corresponds to looking at the Z component of this ball. So what you get is you project the uniform measure on the sphere onto the Z component. Then what you actually get is like this Lebesgue measure. It's this observation by I think Archimedes, that if you take a slice of constant height, then yeah, so the volume only depends on the height of the slice. So actually you get Lebesgue measure. Now if you take the derivative, and there's only one derivative in my case, then you get a Dirac measure here and minus the Dirac measure here. So this corresponds to 1, this corresponds to 0, but I only look at the ones that are correctly ordered. So this corresponds like 1, 0 and to 0, 1, if you like, in terms of these diagonals. And so if I restrict only to the correct order, I recover my spectrum. And the same holds true if I look at more general spectra. So it's kind of clear to see here, because if I make the spectrum that I look at, so this was spectrum 1, 0, but if I mix them more and more, I get smaller and smaller Bloch spheres, which correspond to larger and larger Lebesgue measures like this. and that the general case also holds true. It's a bit more complicated. Okay. And now essentially the idea is, maybe I shouldn't, maybe I shouldn't write down a precise formula, but the idea is really if I now have my distribution of diagonal entries of my random marginals, I can similarly form these partial derivatives, these like du by too many, for each for row A, for row B, and for row C. And I will recover the distribution of the eigenvalues by this. So the upshot is can reduce P spec in this quantum margin problem version to P diag. So I apologize that this may be a bit sketchy. Are there any questions about this idea? So the idea is really I should have written down the name Harish Chandra maybe. So the idea is really instead of studying the eigenvalue distribution directly, and again the challenge comes because we want to study that joint distribution. We look at the joint distribution of the diagonal entries of these marches, and then we recover the distribution by taking these derivatives. And it's not clear to me, for instance, how to make these things approximately true. I'm not sure if this is possible. What is a good way? Maybe this would provide. This would be an interesting procedure to use more generally. So now we can maybe conclude in a second. So maybe I'll just quickly sketch on how we in some of the regime that we naturally looked at was actually the non-asymptotic one. It was like small dimensions where we can explicitly compute this diagonal entry distribution and then recover precisely this distribution of the marginals of the eigenvalues. And so let me maybe just sketch how we did this, or what does this diagonal entry distribution look like? And so the idea is, again, if I take this pure state psi ABC at random, I could first compute the reduced density matrix and then look at its diagonals, or I could first look at the diagonals of this global state in the product basis, which is a classical probability distribution, and then take its marginals. So this is what I'm going to write down. So this is my row. Now, what does it mean to look at the diagonal entries? So I first look at, the diagonal entries in the product basis, which is this PABC. And then I trace out, which is just a classical trace. So it's like, for instance, I have this PA. So PA, which is the same as A row AA, I can now write as the sum over B and C of PABC, and so on. Okay. But now, if this guy rho is chosen at random, then this will be a random probability distribution. It's actually Lebesgue distributed. It's uniform distributed in the probability simplex. So this is so if this is chosen according to this Liouville measure or Haar measure or whatnot, then this is Lebesgue on the standard simplex of probability distributions, of joint probability distributions. And this is just some linear map projecting us down. So what I'm led to is so this is what I do. So I'm led to studying the push forward along a linear map of Lebesgue measure on a simplex. And this is something people have looked at, and for which one can even kind of, where people have looked at, people have looked at the precise, at the structure of the solution. So for instance, what you get is that such a thing will always be piecewise polynomial, which is, so what does it mean? So basically what it means is that a set of all diagonal entries will be partitioned into chambers, so-called like convex chambers. And in each chamber, the measure of the distribution of these PA, PB, PC will be given by a polynomial. So actually, one can write down this distribution efficiently. It's not a priori clear that one can even describe the solution in an effective way, but actually one can. So maybe let me write this down. So the solution will always be given by a piecewise polynomial whose degree one can determine. One also knows kind of how smooth it is. So like if one goes from one chamber to another, so we have this funny polytope from before, and it's decomposed into further chambers. In each chamber, we have a polynomial, and we have formulas basically how we can go over these walls. So we, thanks to a paper by Rosal and Michel Vernier, we can understand the jumps of this measure. And then, of course, we can just take the derivatives of these polynomials directly if they are smooth enough. Okay, if there's nothing singular on these walls. And this is basically how we can compute these random, this distribution of the local eigenvalues. And which I find funny, and I mean, from two perspectives. I mean, the first perspective is that somehow what I ended up with is a classical marginal problem. Okay, if you just look at this here, I mean, here the problem is if you take a random probability, a random joint distribution, the probability simplex, you ask what is the distribution of the marginal probability distributions? It's quite a mouthful. So this is really a classical marginal problem. And a similar reduction is not possible on the level of problem, on the first problem, what I call problem 2, on section 2. Kind of, if you just look at the support of this measure, it will be very trivial. Like if you just look at the set of all diagonal entries, we can't recover the set of all eigenvalues, but we can recover it in this quantitative way. This is maybe kind of amusing. And the other amusing thing is that because I mean, one can kind of easily see that such a put-forward measure is piecewise polynomial. We actually know we can recover, if we look at the support, we know its support is a union of such chambers, of like of these domains, these convex domains. So somehow one sees very easily that the solution to the marginal problem, to this first problem, is at least given by like a union of convex objects, of a union of polytopes. The hard thing is to show that there's only one. So this is kind of the, okay. Was that, so what I mean is, like, if I have this piecewise polynomial and each piece is a convex chamber, like here, then I know that I can recover the distribution of the eigenvalues by taking the derivative of these polynomials. Right? So if this if there's no discontinuities up to the certain order on the walls, then I know that I can recover the eigenvalue distribution just by taking derivatives of each polynomial on each chamber. So if the polynomial is 0, it's not going to be in the solution of the marginal problem. If it's non-zero, it's going to be in the solution of the marginal problem. So the support of the resulting measure will either not contain such a chamber or it will contain the entire chamber. And so in this way, at least one sees that it's like a union of such convex objects. But in fact, one can show that it's only one. Like, so these assemble to give you one convex object. So such a situation cannot occur. Okay, so maybe I should stop here. Thanks very much for your attention.